Welcome to question 4 of the 2019 Mathematical Methods Exam 1 for the Southern Hemisphere. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAA. For question 4, part A, we want to solve the equation 1 subtract cos of x over 2 is equal to cos of x over 2 for x is an element of negative 2 pi to pi included. And I've just highlighted that domain because that's one of the most important things when solving a circular function equation or a trigonometric equation. We need to know where the solutions are going to appear. So another way of writing this is we know negative 2 pi is less than or equal to x is less than or equal to pi. However, in our equation we don't just have x, we've actually got x divided by 2. So I'm going to divide all of these terms by 2 so you can see that we'll have x divided by 2 in this inequality, and when we divide pi by 2, just so we keep everything consistent, we'll have pi over 2, and when we take minus 2 pi and divide it by 2, we'll just have negative pi. And this is going to be helpful when we are looking for the solutions. So we'll just leave that there for a moment, and the next thing we're actually going to do is we're going to rearrange this equation so that we've got all the trig terms on one side. So I'm actually going to start by adding cos of x on 2 to both sides. So on the left hand side, I'll just have 1 is equal to, and we've already got cos of x over 2 on the right hand side, and we're going to add cos of x over 2 to that. So we're actually going to end up with 2 lots of cos of x over 2. Next up, we want to divide by the 2 so that we've just got cos of x over 2 by itself. I'm going to write that first, so we'd have cos of x over 2 is equal to 1 divided by 2, or a half. And we should recognize that that's one of our exact values for solving trig equations. So next up, I'm just going to put a unit circle here so you could draw a quick one of these in your exam to help. And we want to locate where cos is equal to a half. So cos is read off the x-axis, so cos being equal to 1/2 is located about there. And from there, we know that we need to be either at this point on the unit circle or the point down here to get cosine to be equal to a half. And the angle that we'll require to get there is going to be the largest angle of pi on 3. And if we come back to the domain that we'd written up here before, this actually tells us that we can go pi on 2 around in the positive direction. So if I can continue that arrow around until pi on 2, you can see we don't get any more solutions. So instead we have to start heading backwards, and we can go negative pi around this time. So if we start heading backwards around to negative pi, we need to see if there's any more solutions going in that direction. And there is one more solution. So there is another solution that's here, and that angle there is going to be negative pi on 3. So if I summarize what we've just found over here, we now know that the angle, which is x on 2, must equal negative pi on 3, which is the solution that we find if we go negative pi backwards, or in the positive direction it could have been just pi on 3. And now the last thing we need to do just to get x by itself is we're going to multiply by 2, and we need to do that to all of these terms. So therefore we find that x is equal to negative 2 pi on 3 and positive 2 pi on 3. So they are the two solutions to part A of this question. From the examiner's report, we can see that almost 50% of students got full answers for this question, with another 29% getting 1 mark and almost a quarter of students getting no marks for the question. And the examiners go on to say that most students were able to rearrange to form a correct expression. However, some students did not identify the correct reference angle, which was pi on 3. The other thing that students made a mistake with is that many of them did not account for the restricted domain. For part B, we consider the function f, which goes from negative 2 pi to pi, which is the same domain as what we were actually considering before, with the rule f of x equals cos of x on 2, and that graph has been shown on this set of axes. We're told that g is going to be a function from negative 2 pi to pi, where g's rule is 1 minus f of x. And we need to label all points of intersection between f and g, and we also need to label the endpoints of g, and all of those things should be labeled with coordinates. So to help sketch this, rather than starting from scratch and finding all the key features, it's actually going to be more efficient to consider the transformations that have occurred. So this negative here that's multiplying the f of x, so it's negative 1 times f of x, is a reflection over the x-axis. And I'm deliberately doing this in grey because if it was a pencil I'd be erasing this out in a moment, but I just want to get a feel for where negative f of x would be. So reflecting over the x-axis, our graph would look something like this. And the next thing we have in this rule for g is the positive 1 that's just here. And what that is responsible for is a translation of 1 unit in the positive y direction. So now all we've got to do for this grey graph is we've got to translate it 1 unit up. So that means we're going to have an endpoint here. And because we've got square brackets, that's going to be coloured in, that's going to be included. This point here that was at negative pi 0 is now going to be at negative pi 1. A point that was down here at negative 1 is now going to be at 0, so it will go through the origin there. And this endpoint at pi comma 0 is now going to be at the point pi comma 1. So that's another coloured in dot because there's a square bracket on our domain. And now before we sketch this graph, to make sure that it's accurate, we can actually think back to what the question was in part A and how that applies to this graph. Because the points of intersection between these two graphs is going to be equivalent to solving f of x equals g of x, where this is the same as f of x equals g of x, which is 1 minus f of x. And then f of x was just cos of x on 2, is equal to 1 minus cos of x on 2, which is the exact same equation as what we solved in part A, where we found x was equal to negative 2 pi on 3, and x was 2 pi on 3. So that tells us that the graph will also go through this point, because this grid line is minus 2 pi on 3, and this point here, which is positive 2 pi on 3. So we've now got a lot of points that this graph is going to go through, which will allow us to sketch it accurately. So the graph will look something like this, and we can just finish by labeling all of the key features with their coordinates, which is what the question was asking for. So this point here we already discussed was minus 2 pi comma 2. This endpoint was at pi comma 1. Here, even though it doesn't ask for the axial intercepts, it is in fact 0, 0, so we can put that in. And then the last thing we've got to do is just label those points of intersection, which we know were at negative 2 pi on 3 comma something, and the other one was at positive 2 pi on 3 comma something. And the trick here is that if you think back to what this equation looked like just before we solved it for x, was actually that cos of x on 2 was equal to 1/2. So hopefully you can remember that from part A. So that means that these y values are 1/2 and 1/2. So now that we've got that blue graph sketched, which is the graph of g of x, we just erased the grey graph, which was part of our working essentially, and that will be the full answer that was required for this question, with the endpoints labelled, as well as the points of intersection, which is what the question required us to do. From the examiner's report, we can see that 37% of students got this question fully correct, and nearly the same percentage didn't get any marks for this question. And the examiners note that students who were successful with this question made a connection between part A and what was expected or required in part B, which is what we did on the previous slide. The report also notes that most students were able to generate a horizontally reflected version of the graph, which is what we did in grey before we finished off our problem. However, some students dilated the graph or did not correctly reflect it in every section that was required. Some students then forgot about the translation or did not label the points specified in the question, which caused them to lose a mark as well. The examiners recommend that students practice sketching graphs with attention to curvature, so the shape of the graph is important. And one thing that can really help here is by actually plotting points, which was a technique that I showed on the previous slide as we were going through part B together.